will introduce.
Okay.
I have been given the honor and pleasure of introducing you.
Okay.
How many people in this audience know cryptography? Or how many do not know? Basic of cryptography. All right, doesn't matter. Okay. Cryptography, in a popular form, runs on two keys: public key, private key, and there is one more key. That is this Wen key. Okay. This Wen key is known as a worldwide well-known cryptographer, and he has got some breakthrough results and very interesting results. Okay, and he graduated from here, and then I would like to just tell one very amusing, ambiguity he faced when he entered US for the first time. Okay, it's about security and cryptography after all. So the custom people asked him whether he has any drugs, and he said yes. That's it. He's held up, and then he was ransacked and found that saridone and antacids and other things, and he labeled them as a drug that put him into a lot of inconvenience. Starting from that kind of a very simple, humble IISc life, he has elevated himself into an advanced research, served in AT&T labs, extensive service in Microsoft, and then he is one of the pioneers to initiate the Microsoft research lab in Bangalore. In fact, whether it has to go to Chennai or Hyderabad or Bangalore or that kind of decision-making process, right from the day -1, he was associated with Microsoft research lab. He is, and he handled the responsibilities, initiated a lot of collaborative activities, and motivated plenty of youngsters throughout his stay. He used this as a base camp to inspire a lot of research activities in and around India. And more specifically with IIT Madras, I had the pleasure of collaborating with him for several years, more than 20 years. I had great collaboration with him. And he was kind enough to acknowledge that this work is with two of my students. In fact, the moment I walked in, he said, "Here are two of your students." And this work, so he encourages a lot of research with youngsters, undergrad students, postgraduate research scholars, and so on, and brings them the state of the art to the table discussion. It always excites the young minds. He will always be in the cutting edge, always 3 steps ahead of the state of the art, and he is also being constantly be moving into the cutting edge research. Today, he is going to share with us some of his excitements in optimization, and this seems to be one of the very trendy area. And warm welcome to all of you. Warm welcome to you, Ramarathnam Venkatesan, formally, and then over to you.
Thank you. Thank you for your kind introduction. So I'm a baby from IISc long ago, and me and Sastri were together, and he'll always come and wake me up at 11:30 p.m. to go have chai. I was like that, and my MAL Tatachar were our co-advisor, and he prepared me to go work with a professor called Leonid Levin, who's a student of Kolmogorov, and he trained me like hell in many areas. And I never applied for a job in my life. I was always given the job first, then I go for interview. So I don't know. If you go to YouTube, there is a commencement lecture by me as to what I can potentially help you with for any kind of graduate. It's available on YouTube. Commencement lecture, Boston University. You can go look for it. So having said that, I've been raised by a lot of very famous people. So I'm going to talk about something. So this research has been funded by one of the really hardcore product group persons, which is my boss. He gave me $500,000 every year for 3 years to develop this theory, actually. I will tell you, this is actually a very huge business in the sense that I believe in extreme mathematics and extreme applications. Not the most of the people are empty intersection, but I want to work on the intersection. But I want to tell you is that this is a very huge business actually, and everything from differential geometry to concentration inequalities, everything will play a role here. Let me start. So this is the optimization. Optimization theory is about optimizing functions, right? But more formally, it should be called. This is an animated slide, and not very carefully. I gave this talk a couple of days, modified version of this talk in Lodha Institute, which is a new research institute being formed. That's where the director met me, and he made me come here. You should look it up because it's going to be a fun institute. So this kind of, I don't think that you've ever seen these three topics, three words in the same slide: differential geometry and complexity of robust optimization, small loss functions. I'll tell you what that is. Previously, the slide is that optimization in the age of AI. Yeah, what means that the primary goals of optimizing functions has been moved to a different one. And I want to tell you, and just to make sure that you will use random walks on Grassmannians, I'll tell you what that is too. So the main thing is that if you have to be a complexity theory, cryptography, differential geometry must enter in modeling analysis of machine learning algorithms where they are attacked by adversaries. So we have to have a new foundation. I'll try to convince you. Normally, machine learning people think that attackers are Gaussian noise generators. I'll just tell you who they are. The co-authors of this book, the student from CMU, Karthik Gupta, he did some parts of the work. Steve Miller is a student of Peter Sarnak, who defined the Ramarathnam graphs. Bhargav is a student of Professor Kondarangan. Kondarangan always introduced me to students. This is a 1 year best, 2 year best, 3 year best, 5 year best. When Bhargav came, told me that this is my career best, you deal with them kind of thing. So then I made sure that he went and got a Ramanujan scholarship in Trinity College, and he had all kind of applications. Then he became a mathematician. And he got a PhD from Bela Balabash. And this is Neeraj Kayal, very famous prime number theorem person, now into these things. This is somebody who was introduced to me by Kumar Murthy from Toronto. There are lots of interesting things going on with them. I think that I'll short. So more specifically, application of an algorithm to finding roots for multivariate polynomials was alerted to me by Neeraj Kayal. For Neeraj Kayal, everything is a polynomial anyway. So I would like to give you, we actually have a lot of results about linear regression, large regression, support vector. We actually simulated all of them and it works very well. Usually theoretical results don't work very well, but this does. So I want to tell you something about this symmetry. So the main thing is that complexity theory, cryptography, and differential geometry enter the world of formalizing the threat modeling and analysis of machine algorithms, also known as AI. So let me tell you what the attacks are. People think that we need to find out optima which are robust to small adversarial corruptions. I will tell you why. But you have to treat the adversaries with respect. They are not Gaussian noise because you see this is symmetry. Gauss is already dead. He's not going to do any attacks actually. So optimization in the age of AI. So basically, optimization algorithm must deal with general smooth functions. Smooth function is the function which has any number of derivatives you want. But you should not assume that usually they assume the convex, strongly convex to prove something. We can't do that. You know why? Because all the AI algorithms, they're just smooth. They are not convex. And if you go to a person like Nikhil Srivastava, when I told him he's in Berkeley, he was in MSR India. He solved this Cartesian conjecture, and they gave him a job in Berkeley and went over there. So we started talking. He said, Venki, you can't do that. You cannot optimize general smooth function. This is true, actually. But if you impose the condition that finding only optima which are stable against adversarial small corruptions, then you can do it. That's the main message. That's the overall summary of this talk. I have to tell you what is stable against adversarial perturbations. How do you analyze it? And I have to tell you what are all the difficulties in formalizing it. So let me tell you what adversarial attacks are. So supposing you're training a model to detect attacks on, if you go to any bank, they will tell you that these large teams have been working on last 2 or 3 years, right, attack detection in their infrastructure, and they will do what adversaries do, don't corrupt the data. I'll give you an example, and then they'll try to evade the attack detection. In fact, there are services you can buy from black market, the dark net, where you can buy services to infiltrate a cloud provider, and they will detect if somebody is using AI to detect your attacks. Then they will actually disengage and go do something else in the exchange. This is the reason is that I'll explain why. The thing is that we need new principles. Why? Because one can train a small language model, whatever it is, publicly available data, and you can use it as an adversary to penetrate enterprise systems, and you can also use it to defend. Same data. These attacks can be generated very rapidly, and it's a very dangerous situation. But the point is that who will win? Attacker, or because they have the same data? Whatever I can train as a defender, the attacker also can train. So you have to have a model reason for it. You have to use random, just like crypto. How do you use it, right? And in fact, this particular thing of stealing computer resources is a huge business. You can actually go to mafia and other people. They'll give you 4,000 PCs for 10 hours for such. This is actually business where they infiltrate all the home computers and you infest it, and they'll rent it for people to do all kinds of calculations. You can do the same thing in cloud systems also. Therefore, there's always a constant effort to find these people. And stealing computer resources is very profitable. If you want to make money and you're very clever and not getting caught, do it. So this is why this is very huge business, and it's a real problem. And if you're a country like India, you have another country. Other countries can actually try to infiltrate you. And for example, if you're running IIT entrance exam, I know this story. If you want to release the IIT entrance exam because just release the credibility of it, all you have to do is hack the system where the system is stored, and then you publish it. The IIT entrance exam will completely lose its credibility. So how do you design the system? I saw how TCS was designing it, but that's for another discussion. So basically, all the infrastructure on which you are going to use something for a common purpose, the data should be held private. You need to actually think about those things properly, because an attack will get you everything you want. So let me give you an example of a data poisoning attack. So here's a stop sign, and that is a interference net. I nodded to it. So I have to make sure that then it look like a stop for a human eye, but car will see speed limit 70. This is the actual attack people have done. So the idea is that you can attack the model, the data that is being used, and you can actually mislead the car. So basically, some people think that all cars can drive by themselves, but not in Chennai, because everybody is an adversary anyway. So this is not something that is. Another idea is that you can post visible things. If you take a stop sign and put that square there, it'll look like yield. And to put that square, it'll look like speed limit 50 or something. Yeah.
But do you need to have the model weights to do these attacks?
Say it again.
Do you need to have the model weights?
No, you don't. This is a blind attack. This is a blind attack which will work for most model training. That's the point, actually. Good question. Thank you. But if you knew the weights, you can own the thing. So, for example, something like Swift is doing all kind of analysis on the data. If you knew exactly what they're doing, you can actually make a lot of money in one day and disappear. So this kind of attacks are very, very threatening. And in fact, using the AI techniques, you can make them very fast. Okay. The landscape, I have to put some symbols because I think that I'm not doing anything serious. You have a function r to the d to r. I want to find a point which is for which f(x) is minimum valued. That's argument notation. It's a critical point of all the gradient is 0 at that point. That makes sense to you. And it's a minimum. It's a critical value of f. Critical value of f is the 0 value of the function. Critical point is the place where the gradient is 0. Right? We can assume that almost all the known machine learning algorithms are reasonably smooth, as they call it in Tamil, Samuthu, right? This is infinitely differentiable. This is the notation. Important notation is CRF stands for set of all critical points 0 of f, which means where the gradient is 0. If it's called last functions, these are all the example problems. Linear regression, logistic regression, linear programming, support vector machines, quadratic program, and deep neural networks. They are all within the, in fact, any kind of optimization is within the purview of the results I'm going to present. And in fact, we have implemented all these things too. We will show you how that works. The deep neural networks, unlike linear regression, logistic, doesn't have a closed form expression. So how are you going to optimize it? Okay. Usual plan of optimization. So all optimization algorithms do only one thing. You start at a point x0, at step xi, you use gradient descent to find out xi minus 20 xi such that you can lower bound the improvement by delta I. Okay, and use some special properties of f to lower bound the. This is almost all optimization algorithm works. So you have one place, you want to go to another place, and you want to guarantee that you'll make at least so much progress. This plan's ways, if you want to have general smooth functions, I'll tell you why. And DNNs are at best reasonably smooth functions. They can be all thought of as some kind of what is called rich functions. There's a book called Rich Functions, which gives a formal accounting of the entire neural networks. They are of the form, the function has a vector A, and if you give an input G, it will compute the inner product and evaluate as another function G, a real value function from real to real to verify it. The whole model training is all about finding these red A's. There are lots of F's like that. You can think about that first order approximation, actually very good approximation. All model training programs, they are all trying to find some A's. Any questions on this so far? Because, okay, it's too clear. This plan fails, but you need the convexity property for the second order term in the Taylor series. That's everybody does that, because the plan fails because generally the functions are just smooth, not convex. Let me show you an example of to fix a notation. A linear regression is a thing that you're given a bunch of these red points, and you want to draw a line so that the distance from the line to the points when it's someone squared, it will be minimum, right? The least square program. You have to find the AX, given the matrix A and B, you find X such that the f of X is minimum, right? This is a linear regression. Yes, sir.
What are the set of, what is the class of functions that rich, that can be modeled as a rich function?
If they are dense in this set of all smooth functions, you can pretty much approximate any continuous function.
Okay.
That's what you're looking for? Yeah, it's basically about density. So you know the notion of density, right? Say it again. Same thing. You got it. So the notation is f is called the last function, a is called the data. This function is called, the f is defined by this data a, we call it f sub a. Okay, that's a notation. That's a function you're optimizing. So this is the classic linear regression problem. Find the line. There are higher dimensional versions of it, find the best fit plane and things like that. I'm not making fun of optimization routines, but I'm trying to say is that this is that's how I got. So I'm going to tell you what robust optimization in a very quick passable. So FB a loss function with data matrix B. So that somebody if FB is for FB the optimal point is XB star where it minimizes, and suppose Bob is a fraud analyst. I'm telling you how this comes about in practice. He has a data matrix A and he has a X star A for classification. He solves a linear regression and a logistic regression and uses the vector S star A to do all kind of classifications. If you go to Wikipedia, it tells you how to do this for logic regression very nicely. But an adversary who can see A, he perturbs it with the matrix delta. And his goal is keep delta as small as possible, but you move the corresponding solution very far away from his X star. So his deduction will fail. It's a very brief summary of how these kind of algorithms are used. The adversary idea is to corrupt the data mildly and just make the analyst fail. So small, but this delta is also adversarial. A is also adversarial. Typically, they'll assume delta is noise. So the requirement is that if the delta norm of delta is very small, you want the distance between the perturbed solution and XA to be very small, so that you can still have a chance of classification. Any questions on this definition of a robust optimization? Okay, it's very clear then. So in order to achieve this, you have to give the minimum. Finding the minimum, um, like Nikhil was saying, that you cannot do it for there are lots of negative results, and when you also have to use the existing routines, you cannot write all the ML routines, right? I'm going to point out why this is a very difficult thing to formulate. So first of all, I'm going to talk about black box optimizers. So if you want to optimize a function R to the D, I will take a black box which gives us takes as an input a k-dimensional subplane in R to the D, and output a solution which is the minimum for this particular within the subspace. So this is our you can actually easily rewrite any optimization algorithm existing in the available. You can make it to look like this actually. It will find only optimum within this one. So x eta is the minimum of the function inside eta. So this is the only notation I'm going to throw at you. So the advantage of this machine is that you can use any existing routines to make it robust, so that without having to rewrite anything. And if you want to rewrite everything in the AI world, good luck, because it's not going to be possible. So this is the black box optimizer. So one of the things is that you cannot imagine anything about how this minimum is found. So I'm going to give you a very quick overall outline of the entire algorithm. To optimization a smooth function, you fix an accuracy parameter epsilon a, okay, and you pick a random k-plane, which is called eta, and inside R to the D, you give it to the black box, and you get a solution x1 inside the plane, okay, and the critical value there is z1. Now choose eta1 that contains x1, going through this, and you find a minimum in that one x2, and you repeat until you do not make any progress. This is the entire algorithm. So
how do you know when to stop?
when the tau continuous steps, no progress. The progress is there's a accuracy parameter. All the improvements are less than epsilon a.
Sample again, would you just stop even if so you're randomly sampling the new plane, if I'm not wrong.
Yeah.
Then
No, that contains a previous optimum.
If I were to stop now at a given point, at a given plane, does that mean that I would have sampled say 20 planes and been making progress in all 20 of them?
With high probability, yes. You stop and you don't make any more progress, but tau is a small constant. You should not make. That is because I have to prove something which is complicated otherwise. So there's a non-compact version. I will tell you why it is non-compact. So you take the eta and get the x1, but when you do the next time, you actually pick a k-dimensional subplane and add to this an affine plane, and you find the minimum in it. And this is a non-compact version. The same thing. This is used in some kind of proofs which are actually important. So you take a point, and if there's a point inside the line, and either you can contain a line which goes through the origin and the point, or you can. That's a previous version. Now what you do is that you pick a line and then shift it by the point. Any questions? Yes.
So on which parameter I have to select the k means how can I decide what will be the value of k?
Oh, I'll tell you that. Okay. It actually comes to. It cannot be 2. It cannot be 1. In some cases, it can be barely 2. The theory supports more than 4. But it works without 4. Glory to you, but I can't prove it. So how do you pick a random plane? I want to tell you what that is. So consider a set of all k-dimensional subspaces of R to the D. It's called a Grassmannian. And if O of n is a set of all orthogonal matrices, GKD is a compact manifold, which is a homogeneous manifold, which is like quotient of O of n by the product O of k and O of n minus k. So it's a homogeneous space. The intuition is that in a homogeneous space, every point looks the same as every other point. So then the theory says that there's an invariant measure. It's very close to some kind of manipulation of Gaussian matrices. What the idea is that R as an invariant, R as a measured length, which is invariant in translation. The Grassmannian has a measure which is invariant under orthogonal group multiplying it. So it exists, therefore you can pick a random plane, well justified. Any questions? Yeah. So there are lots of papers written as to how to pick a random point on a Grassmannian. There are many, many papers. It's a very nice paper. Very, very nice topic. So all we have is now a random walk of eta 1, eta 2. But eta 1, eta 2 are points in GKD because the GKD is the manifold and the sequence is a random walk on GKD. That's the main point here. So you're having a random walk and the set of all, if you remember it, GKD is the set of all k-dimensional subspace. Even though it has so many, it is a compact manifold. And it's a random walk on GKD. Just to think of it as a sequence of random planes, right? On from the GKD, and the values are this. It turns out that these values Zi's, one can show they form a submartingale, semi-martingale, and therefore it'll converge to infinity. There are a lot of things you can infer from that. Yes, sir.
Sorry.
Please keep on asking.
So this is are you referring to the Grassmannian bundle over Rn? Because
Yeah, you're right. You're right.
yeah, because the point is changing.
No. So no, eta 1, eta 2 are actually points on GKD. The non-compact version is a fiber bundle over that one. I didn't want to get into that.
Okay.
You're right. So when I started working on this, almost every one of my colleagues did not understand how could you start from a random plane and go to the plane that you want, right? There was a repeated question. The only person who really understood it immediately was Michael Friedman. He's a Fields Medal winner in topology long ago. He kept on encouraging me, actually, saying that the kind of thing that I'm trying to prove, people like him and Stephen Smith, another Fields Medal winner, tried to do it. What did they want to do was to bring differential geometry, which studies critical points, to the optimization theory with concrete bounds. They got nowhere, actually. This is where the money slide is for you. There are lots of papers with negative results, and the most difficult theorem to prove is the wrong one. So adversary knows your data matrix and they can choose delta and can use it by 3 plus a plus delta that you assume. This is called the data poisoning attack, right? And however, the adversary does not know my random choices for the planes that I'm picking. And this is bounded. So this particular model covers all the poisoning attack. And the only thing is the adversary does not see my planes. What we do is that we consider the function f of a plus t delta, which corresponds to corruption of a by t delta, where the t is a strength parameter that you can keep increasing. Then the point is that this actually goes back to originally to Einstein's theory of general relativity, where you have to express everything in coordinate independent manner. Otherwise, the theory doesn't work. And the point is that this algorithm very much mimics many of the physics algorithms everybody else has for another time. But one important thing is that the algorithm looks at the minimum inside a plane as well defined, as independent of the coordinates of the plane. You have to only use data which is independent of the coordinates. And that particular thing allows the algorithm to use random coordinates, and the adversary, done every step you can argue and prove that the adversary doesn't learn anything. If it's not coordinate independent, for example, if you go inside a K-plane and do 10 steps of gradient intercept and give it the algorithm, that will leak your coordinate system. There's nothing to prove there, actually, after that. So when we say find the minimum inside a plane, it's a quantity which is defined on the plane and it's not dependent on the coordinates. So that's what is really important here. It has to be defined on the manifold. So manifold is, you can only study quantities which are independent of the coordinate charts. So where does the robustness come from? The random walk cannot distinguish between smooth functions away from any dense subset from this. It's so basically a dense subset of smooth functions. But for example, Morse functions, I'll tell you what the Morse functions can approximate any smooth function's arbitrary accuracy to arbitrary derivatives. So, for example, we can assume its function is Morse, and that completely simplifies the critical set of critical points, which I will show now. So, before you go there, you have to understand the really big animals hiding under the bed. You cannot, if you want to say, I'm going to go to the set of one of the critical points, for a smooth function, the zero set can be arbitrarily bad. It's an exercise in Baby Rudin book that you can given any closed set, I can design a function f such that its gradient will have exactly a set of zeros on that one. In particular, it can be a Cantor set. Cantor set does not have any interior. It's like empty interior. My recommendation is to look at politicians there. It actually works even on manifolds. This is the exercise and the thing. You can actually make any kind of level set to be close set to be a complex. So basically, you have to really simplify the critical points. And the thing is that so basically, normally in cryptography, you want to say some adversary cannot do something, you propose a hard problem and you have to prove it. You can't do it here because these are continuous functions with smoothness properties, topology, everything. In the cryptography, every attack that works because we found a good norm. So good norms and attack is best friends. That's the only thing you want to say. Yes, sir.
So you're going from subspace to subspace. The idea is that speeds up the process because you're jumping from the best points within one subspace to another.
Yeah.
So the dimension of the subspace will play some role.
Yeah, it does. Yeah.
But even so, you might not cover the entire space.
We don't have to.
You will still be starting
No.
from larger dimensions.
No, we proved that it can't happen.
It cannot happen.
Thanks to what is called a property T, will actually come. But before that, I have to tell you that you cannot use it. There's an adversary. I cannot use cryptographic assumptions for it because these functions are smooth and they have norms. Every one of the cryptographic attacks is made possible because of better norms. I've given some details. I'll skip that. So if you don't have detail there, is that ML problems have nice geometry and norm defined in R to the D, and one has to respect the geometry. And norms are attacker's best friend. So, however, there are something problems we cannot solve. There are physical processes in which a small perturbation will send you very far away, like in weather forecast. Those kind of things cannot be covered by this algorithm. But if you're looking at this room and I light up a cigarette here, it's not going to blow up the temperature. Temperature of this particular thing, a minor perturbation like smoking here is stable. It will actually stabilize. Almost all physical processes are like that. In fact, in physics, you can only measure quantities which are not unstable. And that is why there's a theory for it. This makes creative. This is something I cannot solve, as if at least now. Every other physical system, Hamiltonian system, quantum mechanical systems, they all follow the same rule. So I will, in order to do this, I want to show you that the stability theory and transcendental smooth functions, which is actually a proper study in differential geometry. I will show you how that actually sort of works. And Mather wrote 6 different papers showing all of them are many different concepts are equivalent in stability. So with that, I want to tell you what the real problem is. So if you have a critical point x for a particular function, if you slightly perturb it, the critical point may completely disappear. And so you have, if you want to really be stable against small perturbations, your algorithm should not go to those actually. But they may be way better than any number of any other critical point, so you cannot give a bound. In good cases, yes, a critical point may, after perturbation, may split into 2 different critical points very close to each other. This is a very wonderful book to read about singularities of differential maps. What do we give up on optimization? So the idea is that if you have a point x star at which there's a minimum, you can introduce another point, far away point, in which the minimum will be exactly the same value using traditional differential geometry and local coordinate systems. I've given it here. So there's no way to argue that your algorithm cannot go to the imposter things, or you cannot say. So basically, sometimes since we are saying that we are not going to go to any critical points unstable, the optima that we get may be very different from real optima way down below. If you have a linear programming instance in which the primal solution and dual solutions do not have bounded solutions, those solutions, those linear programs with slightly perturbed, the optima will go somewhere else. And these kind of things do exist. And the standard optimization theory tried to cover all of them. And that's where the problem is. So we are not giving, we are not going to say that we will be within some factor of the best optimum, but we will get the best optimum which is stable. So this is one I want you to understand. So in traditional optimization, you go from xi minus 1 to xi, and you do some property of convexity or something like this and prove the bound. But DNN don't change the bounds. But this is like a guy who's standing next to Mount Carmel College and is serially dating on girls, and you want to improve the next girl from the previous girl. This is the best analogy I can come up with, right? On the other hand, if you use Kashdan's property T, I'll explain what that is. The comparison always at the minimum, global minimum. The reason is because wherever you are, there are a couple of planes which connect you to the absolute minimum in the entire plane. Therefore, since the dimension is more than 1 or 2, it will go through one of them. So the optimization algorithm always has an eye about minimum, and this is like the Kashdan property. I will give exactly what it is in a moment, maybe a little bit later. But it was first used in computer science for constructing expander graphs deterministically, and the property T holds for all compact groups, and it holds for orthogonal group, and then we actually show it holds for quotients. The thing is that the improvements are not local. You lower bound the difference between f of x and absolute minimum as opposed to local. So this is like the person has a particular woman in the art, and you're actually going towards that. So all the optimization techniques are extremely local. This one is the first one, I think, which is not local, but it gives up on finding the absolute minimum because they could be unstable. If you have any questions on it, you have to move at least so much.
I can just keep increasing my function value.
Huh?
I can keep increasing my function value.
I want to go to the minimum. Say it again.
Increasing my function value. Like, just make my exercise worse and worse.
Yeah, but no. I want to make I move at least so much towards the bound. That's what it says. I'm not trying to. Yeah.
So then, if I were to keep increasing my function value, just choose worse and worse estimates. That inequality is always satisfied for all.
Correct. I don't want to do that. You want the function to continuously glow down. What I'm only pointing out is that the property T inequality will allow you to compare the current value.
So that's along with something else.
Yeah. Thanks for asking. But I'm going to give you 5 rupees for every question. So this is something which always has sight that is my optimum and keeps on moving. This is something I never expected this algorithm to do, but it does. So now, just to make sure that you don't think that I actually wrote everything down, this is actually cut and pasted from a book. There's a notion of stability. I'm going to disclaim to this. This is all in manifolds. So consider two functions f and f prime, which are continuous continuously differentiable maps from the space to x to y. Okay, and these are considered equivalent if there's a coordinate change x and coordinate y, so that they become equal. That's the definition of equivalence, and that means that the function f and f prime are essentially the same because you're supposed to be independent. All the differential geometry constructs are supposed to work without any reference, shouldn't depend upon the coordinates. A very natural definition. And then the definition is that if a function is stable, if a set of all functions are equivalent to it, form an open set inside this neighborhood WF, such that each f prime and WF is equivalent to f. This is the definition of stability, meaning that they are all bunched together. Huh?
What is the topology now?
Next page. Next page. Next page.
Okay.
So the reason why this is a good notion is because it is equivalent to tons of other natural ways of defining these things. All the proofs are Mather wrote 6 different papers. They're amazingly good papers. The problem for a person like me is to extract the soft concepts and make it a quantitative bound on runtimes. That's a big challenge in which everybody looked at before. But this is the correct notion. I'll show you how we use it. Topology is that one, Whitney's C infinity topology. So I'm going to give you a crash course on C infinity topology. I was just explaining it to the director, Nagarajan. He knew about jet maps, so that was easy. So the point is that two functions g and f are mapped to the map j to the k to each if the Taylor series agree up to kth order terms. The idea is that j to the k, you can think of it as the first k coefficients of first k terms of the Fourier series and of f, and the first k series of the Taylor series. If they're equal, then this is the map j to the k tells you this, and then we're using this. If you say the distance between j to the k, the Taylor series is a truncated function, you can compute distances between them, and if it's less than delta, they belong to the neighborhood. So the idea of jet maps are a way of taking a smooth function and extracting only the first k Taylor series terms and comparing them, and they agree that they're supposed to be the same. But if they don't agree, then they find the distance. That has a distance metric. But the space C infinity comma xy is not a meterizable. You cannot add any metric on it. If you look at any kind of applications in audio, video, text processing, and all everybody's doing it, they'll use 4 or 5 metrics. And then you get something. It's like this space is a Fresher space. It's not meterizable, but what you can get is countable number of semi-norms, which can be used to induce a metric. So I think this is something everybody has to realize, that you cannot meterize audio, video. They are not meterizable. So just one take-home thing is that you consider two functions f and j to be equal under the map j to the k if their Taylor series agrees up to k terms, and then you can compare them as functions. And this is called a Whitney C infinity topology. And then you can get a ball. This is the way you do the open sets. Okay, good. I will come to that a little later. And I want to say that there's various definitions of stability. They're all equivalent. And if you go to this book, they're going a very nice accounting of at least 3 of them. So I'm going to tell you one particular way to approximate them. So if you have a smooth function, the critical point of f is called a non-degenerate if the SCN second order term is non-singular. Okay, and this particular quantity, this particular statement is independent of coordinates. The value of the estimated SCN is not. Yes, question? The function is called a Morse function if all its critical points are non-degenerate. Now, it's very, very funny that you can get, so you can take a function f of x and add a linear form a, xi in local coordinates and call the set B where this function is no longer Morse in the neighborhood. You call it's called the bad set B. But the theorem of Sard shows that this set has measure 0. Absolute measure, it's a null set. So it allows you to pick A to be arbitrarily small. If you add a very small perturbation to the function f, the f will become Morse function, where all the critical points are non-degenerate, and then that function will have only finitely many critical points on a compact manifold. Dramatic simplification of the critical point construction, but the f is extremely close to little f. Any questions? Morse functions are designed by Mr. Morse to study topological objects. They are not supposed to study the optimization theory. But it turns out that you can do coordinate changes and write any Morse function around the origin as a sum of 2 squares, difference between sum of squares. It is not, if you take a Taylor series, you can get up to second order term and then some errors. This is exactly equal to that function after a coordinate change. The one corollary is that around origin, for a small neighborhood, only 0 will be the critical point. Therefore, all the critical points will be isolated from this neighborhood by at least some quantity, which means that the critical points of f will be discrete, which will make it finite and a compact thing. So This is a very dramatic simplification in the structure of critical points because it could be granted set. Any question? Extremely clear. So this is our main theorem, first theorem. So give me any little function f, and you consider capital F to be a Morse approximation. Then for every critical point of the Morse function, there exists an arbitrarily closed critical point of little f, such that the value of f of x and f of x prime can be made arbitrarily small. There's something called inverse function theorem. You have to hack it like crazy to get this result. The proof is that there's a very long proof. It says that if you do the random walk, it will converge the critical point of f. It won't get stuck anywhere. And to make matters worse, we can actually give a runtime bound, which is polynomial in the accuracy parameter a, and what is called the variance of the function f. If a function is constant everywhere, there's nothing to optimize. If the variance is more, then that means it can optimize. And it's a very natural parameter to do. And there's another theorem due to me and Stiemüller, which actually removes that condition. It's a pretty complicated thing. I'm not going to say it. So, but however, we have a constant runtime bound. This runtime bound is such that it will depend upon f and something, but I won't be able to put a particular number on it. I would not be able to say if you do linear regression, it will run in d to the power 4. No, some constant. That's the best we can do, because in order to estimate those things, you have to do crazy integrals on manifolds. I don't think anybody can do it. So, yes, sir.
So how do you define variance of f?
Variance of functions, the very, very similar way. It's an integral of f minus mu over the entire manifold. So because there's a invariant measure defined on the Grassmannian, and therefore you can do integration, which is you can take as the average value for the function. The variance is nothing but f minus average value to the power square integral of the entire manifold. The fact that it's well defined is a long exercise to check.
One question. So, how easy is it to, with respect to the Hall measure on the Tasmanian, how easy is it to first compute the Hall measure?
We don't have to.
Okay. So the variance and
These are all just used in analysis. The algorithm was doing just the random walk.
okay, so even in proofs and all, it is not necessary to compute integrals.
No, I'm going to just say that if the variance is polynomially bounded, then the algorithm will be in 1 over the variance. But there's another theorem that doesn't depend upon the variance. But that is monumentally long. So I wrote a paper about this. It was 85 pages of analysis, and there's no way any one of the conferences are going to read. But this is something actually unusual, because differential geometry is a very soft concept. For all epsilon, there is epsilon. You have to get a runtime bound. That is not known before. So I want to give you a perspective here so that you think about this in a different way. So there's a person called Spielman, Daniel Spielman. He was a student at MIT when I was doing study. His algorithmic research always implements things. This is what I do too. So he wanted to find out why the Danzig's simplex algorithm never runs too long. Although there are some worst cases in which the linear programming app will run in exponential time explicitly. You can construct it, it will run only in exponential time. So Spielman's intuition is there's a matrix here that is given to me. That's the worst, but we only see a plus delta because all the coefficients of the age are getting rounded in some physical process. Therefore, they are added with some Gaussian numbers, the IID Gaussian. Then he proves with this particular a plus delta, the number of facets in the simplex is polynomial, and you can find the best result for it. And thereby, for the first time, giving an explanation as to why simplex algorithm, which should take enormous amount of time, runs always quickly, and the interior programming method, which is supposed to always take polynomial time, takes too much time. So I didn't say that one, but this is it's a really beautiful result. He got prizes for it, and he deserves it. It's a viewpoint. It's empirically why you never get a worst case input. At least it's jammed to the Gaussian. The dual version is tau is a Fields medal winner. So if you take a random n by n matrix and fill it with the Gaussian entries and look at the singular values, then you can fill it up with plus or minus ones, compute a singular value. You can put any kind of distribution and obeys it, the fourth bound. They prove that all of them will have the same type of singular values as matrices become bigger and bigger. It's a very nice paper. It also has a what do you call it, appendix written by one of the IISc staff members. Really beautiful paper. The appendix is even better. So he shows that this particular research started because long ago, when people started finding out the energy patterns of hydrogen atoms and other atoms, when you plotted it, it actually looked like singular values of random matrices. And that's why the study of random matrices took off. And and then they're finding the same kind of critical values for every one of them. And there is this guy, Peter Sarnak, who actually showed that it actually is even the zeros of zeta function have the same kind of patterns. But what they show in the paper is A is random, but you can add a deterministic M, but you get the same singular value. So here is worst case matrix, random noise. Here is a random maze with deterministic, not adversarial noise. Both of the, so this is the kind of way in which people are trying to explain things. But the approach that we have actually subsumes both of them. And the claim is that it will converge to a critical point of Morse approximation. How much time do I have? Minus 5 minutes?
Another 5 minutes.
Okay. So I haven't given you any proof, but there is proof written there. But Nikhil Srivastava forced me to give all the proofs in Berkeley. One of the main important thing is that there's a simulation argument. If you have a black box for little f and black box for this Morse approximation, there's a mathematical proof which saying that the execution trace will be extremely close to each other. Therefore, our algorithm cannot tell one from the other. We call it co-convergent. And this is for step 0. We have to really there's a book called Applications of Inverse Function Theorem. This is available as a book. We have to take another inverse function, implicit function theorem, and then completely rehack it. And the second one is you have to you have to really study the Taylor series on Lie groups, and then you can prove the lemma. The Custon property, I'm going to tell you what that is. If you have a function f defined on where's the bulb? You have a function f defined on f on a manifold, and you move the vector by multiplying by a matrix, random matrix O of n, the matrix O of n, singular matrix. There is a lower bound on f of x minus f of gamma x. That is the Custon inequality, which usually only for groups. We extend it for all the quotient groups also, quotient maps also. And then we also can talk about using martingale theory that there's an x infinity distribution, and the distribution will be seen when the algorithm stops. So these are like a characterization of anything. And I'm a big fan of the concentration inequalities lectures produced by this department. He's sitting right there. There's a very clear case. There are bulk of the things that are being used in further analysis of this algorithm from this one. There are calculations you don't want. Well, so basically, to your question, what you prove is that from alpha, it will move at least so much like that. And this is where the property T inequality comes. And property T inequality is produced for compact groups, and the equality comes on Grassmannians. It's available O of n and Lie groups of dimension more than 4. And it doesn't have to be compact. And we use the non-compact version also. So in order to show that you make progress, you need something like property T. I can't prove that you can without it, but I can try that later. So I want to tell you something about Neeraj Kayal. So Neeraj Kayal was visiting Redmond, and he always likes only polynomials. In fact, he knows all the polynomials personally. He said, I have a polynomial in 100 variables. You're asking me to find a root inside a 50-dimensional subspace. That 0 will be completely random. What's got to do with the original 0? So what it says, the property T implies that if you keep picking up planes over and over again, you will get to the minimum. So he couldn't even wait in the airplane. He programmed it, and it worked very well. And ever since, we've been working about that. So there are some experimental results on this one, and there is something called a matrix multiplication tensor. I can describe all of those things, but I will stop here for questions. So there is a lot of implementations of these things. Questions? Yes.
I was trying to understand the duality between the tau result that you mentioned and also the Spearman test.
So in the Spielman, right? If what you see is an adversely generated A, then there are cases in which the simplex algorithm will run exponential time, but you never see it happen because empirically there's a truncation error of each coefficient, which is modeled by adding Gaussian noise to it. In that case, it collapses. Whereas in the tau and wu, there's a random matrix. It's got a singular value distribution, but you can add a deterministic corruption to it in many situations, and they show that the singular value distribution will still converge to the same thing. So one is worst case matrix with random noise, and the other one is random with the deterministic noise. This is they're trying to cope with data where the original input for data matrix comes and where is the attack comes. So there's a dual notions of it. Worst case and random and deterministic. Yes, sir.
So thanks for the talk. Your algorithm basically involved. So your algorithm, as I understood, found the random thing, sampled the random subspace, and then found the maximum there.
Minimum, yeah. But the next plane should contain it.
Sure. So is it morally sort of equivalent to thinking about doing, let's say, stochastic gradient descent, where you restrict yourself to moving the direction?
No, it is not. It is not. That space doesn't have anything like a property to analyze it. And in fact, in practice, it won't work. You can do something like this in 2 dimensions. It will work in some cases, but the point is that if you have the function defined in a big space, it may have a variance here high, variance here low, variance here high, and things like that. And then if you pick enough samples, you can get something like that, but you wouldn't know when to stop. Whereas in a homogeneous space, every point looks the same actually. So you have some kind of uniformization so that you expect that if you make a few samples, you make a progress.
How do you exactly find the optimum along the subspace?
I'm assuming that it's given a black box, and it's a very fair question. And it actually, you can use any kind of a gradient descent package implemented by any kind of algorithms, but I can give examples where it'll get stuck actually, and we won't. And so because of this, so let me answer it carefully. If you want to find out, so n is equal to 1000, k equal to 50, I want to find out a minimum inside the 50-dimensional plane. What you do is that you have a point x, right? So you create something like many subplanes of that one of dimension 20 of many of them, and then you find the minimum in all of those containing this one, and you consider the value statistics, order statistics, using your concentration methods. They actually separate. We have an approximate proof, and we're verifying that it actually works in practice. That way, this will be a first time you can actually give a theory how not to get stuck in saddle points and local minimum. So this is something Neeraj Kayal made me think about, and so it's mainly so. Whereas the property T is walk is funded by property T itself, whereas in that particular case it's purely by concentration of order statistics. Did I answer it properly? Thanks for the question, because I wanted to mention the order statistics and concentration. Thanks. Okay. There will be coconut. Coconut and banana.
Yes, it's true. It's my pleasure and honor again. Thank you very much. Thanks for an interesting talk.
Yeah. You can freely write to me anytime you want, and I always talk to all the students. Huh? In my disk drive. The reason is that it's 85 pages. I'm trying to contain it into smaller self-contained. It moves from differential geometry to Lie groups and all these kind of things. I'm trying to compress it. We're almost there. I can give you the existing version. Yes, the proof exists. 85 pages. Yes, sir. Please. I may ask as you want.
You showed the matter stability result. I didn't quite get how that becomes useful.
So the stability as a good question. So I only stored stability. A function is stable if all the equivalent functions in an open set, right? That notion is equivalent to if you take a function and corrupt it with a bunch of functions to it, then it remains stable under this one also. That these notions are equal. So we are more interested in saying that a function corrupted by adding something, right? These two notions are equivalent from a theorem of Mather. That's how it becomes useful. I have to refer to that one, but you've read Mather's papers?
I've read a little bit of that.
But there are 6 papers in which many are thought to be equivalent.
It's not my expertise.
Yeah, recently somebody found a very simple version of 20-page proof of one of the equivalences. It's actually very readable.
I never read one of those proofs by that.
Sorry. But my job is to read them and get quantitative bounds. Because those are soft notions. For all the epsilon, there exists delta. Yeah. Yes, sir. Any questions? 50 rupees for any questions. Just kidding. 100 rupees. Okay, good question. It cannot be one because in order for the algorithm to work, you must be able to argue that there is a plane, k-plane, which goes from your point and the absolute minima. If there are more than one of them, it has to go through some of them. So it has to be the O of n orthogonal group as property T for n greater than 4 equal to 4. So 4 is a good criteria, but for many of the concentration results that are coming here, it has to be about log n, log the dimension. So basically, maybe, see, there are correct results and provable results, right? And Danzig algorithm is correct, it's working, but if you want to prove it, you have to do all kind of things. So for proofs, for certain quantities, you will need something like log D, although for some of them 4 is enough. But not one. No, not 1 or 2. So you maybe know that O of n is as property T only for n greater than 4, equal to 4. Any questions? So I want to tell you, this is actually core for all the AI and other things. It's not the only domain. You can actually use this technique to solve partial differential equations. And Navier-Stokes equations, Schrodinger equations, they're all being solved using the AI techniques actually. So it's got a huge scientific component. It's also used in medicine. And in all of them, you need to actually have a method which actually works, and you have to know it will work. Right now, everybody's hacking actually. So basically, this is just the first shot. I claim that this is actually a $1 trillion business actually. Cover every one of the areas. I can't give the $1 trillion, but it governs $1 trillion. For example, even if you can solve Navier-Stokes equation, which governs all the fluid mechanics, that is it's basically used by every industry, aeronautic industry, everybody. It's also a Mendeley problem to prove that Navier-Stokes equation work can be solved for dimension 4. It's not known. And this algorithm can also be used in things like, gravitation and quantum mechanics, all these kind of things. They're very similar to them. They're all inspired by them. I cannot explain why, but. So this process that comes in the algorithm is very general physical process. It's called action principle. If you go type Wikipedia and type action principle, you will see all of it. That one is asking questions. Oh, went away. Thanks. Any other questions? Thank you.